Okay, so we are continuing our last discussion, which is we discussed that there are several other polymerization, and for example here we have um, so from the discussion on ionic polymerization, we see that we have cationic and anionic. And when we discuss on anionic polymerizations, we see that one phenomenon that is inherent with the anionic polymerization is that they are actually always polymerized and not easily to be terminated. Okay. So the question next is if we can control the radical within the radical polymerization. We can control radical and treat the radical as they are living. Okay. So we can adjust like easily and we can tune the property as we want. Okay. So this is what we call the living radical polymerization. So the principle here we have several strategies. This is the first strategy, which is to strongly reduce the concentrations for the radical itself. And to be able to do that, we are taking the example here, which is the atom transfer radical polymerization. That's our first strategy. So within this scope, we are going to shield or to cap the radicals. Okay. So basically, what we are going to do is we are going to use a metal complex, okay? And then this is act as the cap, so it will shield the radicals. So this metal complex will go through this radicals, and then it will cover the radicals, and then we can see that it's basically it seems that it's removing the radicals, but in truth, the radicals still inside here. So which means that we can activate it again and make it polymerized. So when it is in this propagation state, it can polymerize. And how to control this reaction is we are going to push the reaction to the left side. So while it's polymerized, within certain times, it will go to the dormant state and it will basically sleep. But we can initiate again if we want to make reactions. Okay. So that's the atom transfer radical polymerization. So we the transfer is between the metal complex. Okay, the metal complex. So you can see from this steps, and this is some of choices for the initiator. So we are going to select initiator based on the halide. So either chlorine, bromine. Okay, I think they are the common one. So bromine and chlorine for this FTRP. Okay. Okay, and then this is the more general reactions. So we see that this metal complex here, that metal complex is the one that covers the radicals. And if you want to polymerize, we go here, we have the radical, and we can polymerize. We can polymerize until maybe some repeat unit, maybe it's long enough. And I think we can control based on how much concentration we have. Okay? How much concentration we have for the radicals. If we can suppress or reduce, then the time to get into this dormant state may be shorter. Okay? And if we have more, then this is going to be longer. Okay. So we call this transition metal catalyzed radical polymerization, or just simply atomic transfer radical polymerization. Okay. Or this is the other name. Because it's only, I think, within this case, it's only applied for metal complex. because it can easily cover the radical. Okay, so all the kinetics, I will skip that part because I think too much complexity within this course. So just overview on ATRP, I think that should be enough. Okay, the second strategy is we are going to take this into what we call the, let's say it's strategy 2. Now strategy 2, let me write more clear. So strategy 2, this is rapid exchange. Of radicals. Okay, so there are only two strategies. Strategy 1, we take cover, okay, take shielding, so the radicals is covered by, in our case, the first strategy by the metal complex. Now we have strategy 2, which is the rapid exchange of radicals. So what is rapid exchange of radicals? Based on the names, we are going to see that the radicals will be moved very fast, okay, so exchange very fast. So the principle here, it will be very efficient. So the chain transfer very efficient. So that's why it's called the rapid exchange. So because it's transferring the radicals very efficient. And the second principle is the concentration for the radicals. It's still there. It doesn't change. Okay. We call the method for this strategy 2. We call the radical addition fragmentation polymerization. Sometimes we call this like RAF. So we are going to see that that fragmentation will plays an important part within this polymerization. Okay, now the steps or the idea, we are going to use some special transfer agent. We call it dynamic change transfer agent. So if we look at the picture, it seems similar to strategy 1, but the difference is the radical is still there. So what's happened is you're just switching these radicals with this, and then this radicals goes here. Okay, so it's just switching radicals and the this transfer agent. Okay, so this one, okay, so it goes forward and backwards. Okay, forward and backwards. So what we did is the steps first. We add the agent, the RAF agent. We add to our radical polymerizations. And then the rate for the chain transfer to this agent will be faster than the termination. Okay? And then the next part is these radicals is always consumed. It's always consumed by this agent. So it will captured by the agent. And then the termination reaction strongly suppressed. You have to write here, let me write, it's supposed to be suppressed. So what happened is, in between this chain transfer, the one that has radical, they can propagate. And it is very efficient. It doesn't change the concentration at all, because basically it's just transferring the radicals, switching forwards and backwards. So we need to have a really special transfer agent, and one example that is really good is esters. We're going to see how it looks like later on. If you want to draw, here is the diethioester. And basically it's good at accepting radicals. Okay, the process for this schematics, for this reversible addition is basically, let's see from here, okay, the first one here. So we see that the radical, this radical here, it will be attracted to the electron on the diethioester. And it will generate the new species, the diethioester species. And then all the electrons will be moved throughout. And basically what we see is we are exchanging this R and some fragments within the diethioester agent. But this fragment will switch forwards with the R. So this middle one is when it's transition. So it goes inside here, breaks the bond. Okay, it has more radicals here, then it will also want to stabilize, the electron wants to stabilize and make it double bond, and then the A is broke down and makes another radicals. But then it is also wants to stabilize and goes here and goes over here and goes forward and backward. And while doing this, in each of the this part here, they can be polymerized. They can be polymerized. So basically, we are going to see how to prepare the initiators, which is we want the initiators to have the radicals, okay? Or we intend to put some other species inside the initiator. Okay, and then I think this is how to see the chain transfer. This is the rough agent. Okay, and you can see that based on what we prepared here, we can basically adjust every species within the when we polymerize. We can adjust the functional groups as well. Yeah, I think this scheme can be overviewed as a general graph polymerizations. So we can see that we can polymerize this, right? And while it's doing the chain transfer. So when the radical here, okay, is polymerized, maybe we can see how much time, okay, and then it's switch again the radicals, and now we have another one here that is polymerized, and then switch again, and polymerize, so switch forward and backward while polymerize both sides. Yeah, so basically we can adjust the species. Okay, we can adjust the species on this M. Okay, so we can adjust. Okay. Some example for some agent. We have one until 9 types, or generally it's 4, but within this 4 we can have subcategory until 9 agent. I think you can just write the category, the diethioester, the tritiocarbonate and dithiocarbamate, xanthanate, or Maddox agents. So basically, this is going to be how we choose between Z and A. If we see from the previous slides here, we see we have Z and A, right? And within the agent here, we have Z and A. So basically that is going to, we can inter-exchange with with this agent here. Okay. So number 1 to number 3, the diethioester, and we call this as diethiobenzoate. This type here, the first one here, is mostly used compared to the other one. I think because it's quite simple, the structure. Because it has the phenyl group. Okay, it has the phenyl group that helps the when electrons shifting. And if we see the number 4 and 5, the tritiocarbonate, this one here, the reactions. So if using the diethioester, we see that Z and A we can switch back and forth. But here for the tritio, we can see instead of 2 places Z and A, we can have 3 places. So we can get this kind of equilibrium. Okay, so we can have 3 pathways. So these radicals, okay, get into the agent, and then switch the radicals here, and it can go this way or this way. So let's say we go to the right side. We go to the right side, and this M2 is becoming radical. Okay, and then it goes back and goes through here, the transition, and then let's say we go to here. Okay, we get another polymerization for the M3. Okay, and then switch back to transition and maybe go back to the first one. Okay, so it can have 3 pathway because of the structure. So we can exchange this 1, 2, 3. So we can see from this double bond, single, single, okay. Double bond, single, single. Okay, so that's the tritiocarbonate that has the unique equilibrium. So I think, let me write the diethioesters. So this is chain transfer activity. So diethioesters, this will be greater than the tritiocarbonate. And this will be greater than, or maybe similar to diethioalkanoates. The diethiocarbamates. And then it's greater than the xanthate. Okay, this is generally the chain transfer activity. So the diethioesters is more likely to be used because of its chain transfer activity. But again, it doesn't say that quality is better this one compared to this one. No, not like that. It also depends on what kind of materials or what kind of polymers we would like to adjust. But in terms of general chain transfer, dipolyester is the best one with chain transfer activity. If you are maybe asked why, perhaps one of the best answer is because the simplicity of the structure, and it has the final group that help localize the electron or shifting the electrons. Okay. Now the third part of the synthesis, the last part, is the Ziegler natta catalyst. We can also say this is one of the coordination polymerization. Which this is going to be related to the stereochemistry. So every time you see the word stereo, what stereo means? Anyone know? Let's say in terms of audio, what stereo means. You have like mono and audio, right? Stereo, like if you see, I'm not sure, maybe some advertisement for audio for maybe 10 years ago, maybe 15 years ago. And when you see kids see the word stereo, audio, stereo, it means that you can hear like from every angle, right? Or if you see the mono, you hear with your earphones. Sometimes maybe you hear from YouTube. Sometimes only one phone, one ear that the sounds can only come from one. We call mono. If you can hear from two, and you see some layers in them of the sound, we say stereo. Right? So stereo, it means that if we see there are one, and then it is equaling to the other side, that become a pattern, we say it's stereo. So stereo is related to the structure and how the pattern will be. Okay. So maybe the pattern have like, it's always going up. Like you have the polymers and you have the side chain, and the side chain has the functional groups, and the same functional groups is going to the top. And we say, we say isotactic, and so on and so forth. Like we have symbiotic, we have another tacticity. Okay. Now, if you heard stereo in chemistry, that is what we relate to, how the structure will be, okay, how the patterns will be. Okay, so it's related to the tacticity of polymers. Or we say the chirality. Okay, and I hope you still remember what does it mean, okay, in terms of chemistry. Okay, so we say what we have learned before, that the ionic polymerizations that prepared specifically for stereoregular polymers, usually they are specific to some types of monomers, which is the polar, that has a polar functional groups, and we say that the method will be not very appropriate for non-polar monomers because they require stronger coordination. So within this scope, within this reason, we need catalysts. Thus, we need catalysts. Okay. So we need to prepare some catalysts, especially for non-polar monomers. Okay. Help you get the polar, non-polar based on the electronegativity. You can also see the polar, non-polar used to describe the surface in the hydrophilicity, hydrophobicity. Okay. So if we have a polar, it will attract it to another polar, right? If we have non-polar, it will attract it to another non-polar. Okay, I think that's basic chemistry. Okay, so wait. So the stereoirregular polymers. Okay, let me explain a little bit here what we are going to do. So if we describe the polymer in terms of the stereochemistry or in stereochemical, at least we have three, right? So we have isotactic, we have syndiotactic. I forgot to put the picture here, so let me just draw for you. And the atactic, right? So let's say we have, let me just copy this so that we have identical. Okay. And then I hope you remember we can write or draw the I think we can just draw one and copy again. I think that's would be better. Let me draw here. So this H, so it goes to your face and goes inside, right? Go outside, inward and outward. I think, let me just move here, make spaces around there, make spaces. Okay. So isotactic, we are going to see clearly the same pattern. Okay. So let me write with the green color. So X, Y, X, Y, X, Y, X, Y. Okay. Syndiotactic, you see the pattern, but alternate. Okay. Syndiotactic is alternating, so we'll say X, Y, and then Y, X, X, Y, Y, X. Okay. And atactic, you see, it will be random. So let's say x, y, x, y, y, x, x, y. Okay. So this is similar, alternating, and this one is random. And basically, the Ziegler-Natta polymerization or catalyst, it will control how the tacticity will be. So we can control to make it into the isotactic. So it will be have a similar pattern. Okay, so Ziegler-Natta catalyst, okay, per definitions, let me define first. So Ziegler-Natta itself is involving the compounds, halides compounds usually, of group 4 to 7 transition metals with organometallic compounds of group 1 to 3. So it has 4 to 8 transition metals with 1 to 3 organometallic compounds. So basically, the Ziegler-Natta is controlling the arrangement or stereo chemistry. My pencils died. Stereo chemistry of polymers. Okay, now there are at least four important things. So if we see the linear polyethylene, it actually can be obtained by a heterogeneous catalyst. And Ziegler-Natta catalyst, as we see before, it's based on transition metal, the halides and organometallic compounds. And we are going to see this number 3 and 4, the insertion reaction that will prevent the side chain formations. Okay? And then for substitute monomers, we can obtain the stereoregular polymers. And we are going to see these 3 and 4 schematic descriptions, how the insertion reaction will occur. Okay. Okay, maybe this one here. the Ziegler natta catalyst. First is formations of active site. So this is formation of active site. Actually, the formation of active site is the first one here. Okay, the left part. Okay, this is formation of active site. Or even to be precise, I think this one is the active site. It's the active site. And then it's prepared to propagate. Okay, so this is the propagation. Okay, let me just make some overview, and maybe we'll see later. Okay, so after the formation, then we see some other steps, which is the propagations, the complex formations. Okay. And within this complex formation here, it will decide its preferred orientations. Okay, so it will decide the preferred orientation, which is here, okay, this one here. This is the preferred orientations. Okay. I think I'm trying to look for the three dimension shape so that you can see more in terms of stereochemistry. It's more, I think, more appropriate. But I think this is just showing you how the site will propagate. The site will propagate, and then it will have the insertion of the double bond into the titanium carbon bond and reform the free d orbital, which is here. Okay. And then it will migrate the organic chain into the initial position. Okay. And it will repeat the process until you get the polymer with the stereo or the isotactic polymers, which is this one here. And you see this will be long polymers, and it will have this same preferred side chain reaction. Okay, I think I will go back here next Monday to get into some details that I missed out within these reactions. Okay, so I will just stop until here. We see later on Monday, and I think because this is one of the last part, okay, that we've done for the polymer synthesis part 4. I think on Monday we can also go to the next agenda, which is I will go through some structure or some architecture that is quite interesting in polymers. So I think that's it for today's class.